Part 1, Sound Pressure Levels and Decibel Mathematics.
In this lesson, we're going to be looking at the various properties of sound or noise. We use those two terms interchangeably since there's really no difference between sound and noise except insofar as noise has the connotation of being unwanted sound. We will also be looking a lot at the mathematics of sound, how to deal with the decibel calculations in particular. This is rather complicated and different from mathematics that people are used to, so it will take a bit of explaining. And then lastly, how the properties of sound change as it travels from the source of the sound to the receiver of the sound, the listener usually. To start at the beginning, let's talk about what is sound. It can be defined as a pressure disturbance in air or in whatever medium it's traveling through. This pressure disturbance travels as a wave outward from the source, and when we say a wave, we're talking about alternating regions in which the air pressure is first increased and then decreased. That is to say, the number of air molecules per given unit volume increases and then decreases. And this region of compression travels outward from the source and appears like a wave. If you could see it, it would look like a rock dropped in a pool where the wave is traveling outward through the water. The wave travels at a fixed velocity in any given medium under given conditions. At standard conditions, it travels at approximately 344 meters per second in air, which is the same as about 1,130 feet per second. In denser mediums, like traveling through metal or rock, it's going to go at a higher velocity. It will also change in air depending on the density of the air, which fluctuates with pressure and temperature. But approximately 1,100 feet per second is a good velocity to use. When we think about sound pressure, we first have to consider what is the normal atmospheric pressure. There are many units for pressure, one of which is pounds per square inch. And in that unit, normal atmospheric pressure is about 14.7 pounds per square inch psi. It's also about 30 inches of mercury, 760 millimeters of mercury, or to use the internationally accepted scientific unit, it's about 101,000 pascals, PA. Now, sound pressure is a fluctuation or a deviation from this normal pressure. As the wave passes through the air, the pressure increases and decreases slightly above and below the normal atmospheric pressure, whatever it may be. Now, these are very small deviations, and the minimum audible sound pressure deviation is usually stated as 0.00002 pascals. Now compare that to the normal atmospheric pressure of 101,000 pascals, and you can see it's a very minute fluctuation, but our ears are extremely sensitive to these very small atmospheric changes. Now that's the minimum pressure change that we can hear. The normal conversation is at a much higher pressure change of approximately 0.02 pascals, but still that's very small compared to the normal atmospheric pressure. Quite often we find it convenient to plot a graph of sound pressure, or at least conceptually, in which the pressure relative to atmosphere is plotted on the y-axis. So above the center line is the compression, and then below is the expansion or the reduction in pressure. So we see that the pressure alternately increases and decreases relative to atmospheric pressure, and this happens many times per second, hundreds or thousands of times per second, and that's what creates the impression of sound. This is at any given point, this pressure fluctuation is occurring above and below atmospheric many times per second. It's not always quite as neat as what you see here, but this is a pure sort of sound in which the fluctuations are very regular. For purposes of measurement, instead of dealing directly with the sound pressure, we use something called sound pressure level. The sound pressure level, SPL, is a logarithmic transformation of the sound pressure value itself. And as we'll discuss, this is a more convenient way of dealing with the pressure unit. If we were to take the mean or the average pressure, if you look back at that graph, you'll see that on the average, it's approximately 0. Instead, the pressure that we deal with before taking the logarithm is what's called the RMS pressure, root mean square of the pressure. Mathematically, the way this is done is to square each pressure value, so the positive ones squared are positive and the negative ones squared are positive, and then take the mean or the average of those squares, and then take the square root of the mean of the squares, and that's the RMS value. If you have a perfect sine wave like the previous graph, this will be about 70% of the peak value of the pressure. At any rate, RMS pressure is nearly always what's measured. And then we take the logarithm of the RMS pressure, and with appropriate mathematical transformation, we have the decibel, abbreviated small d, capital B. The decibel is originally named for Alexander Graham Bell. It was the bell, and then later it was modified to the tenth of a bell, the decibel, and so that's the reason for the small d, capital B. The mathematical definition of the decibel is that it's 10 times the logarithm of the RMS pressure squared plus a constant. And the constant, if we're using pascals for the pressure unit, is 94. This definition is equivalent to the decibel equal 20 times the logarithm of the pressure plus 94. And if we substitute in the minimum value of pressure that we are typically able to hear, which is 2 times 10 to the minus 5th pascals, when we do the mathematics, it comes out to 0 decibels. So that value of pressure was chosen with this formula to make it 0 decibels. Now, in everyday practice, we don't have to worry about all this mathematics and the RMS and all that business, because the instruments do this for us. They have the circuits that will do the mathematical transformation of pressure to sound pressure level. But it's important to understand what's going on when we try to do further decibel mathematics. Let's look at some examples of decibel values to give you a feel for this. As we've already stated, 0 decibels is the normal threshold of hearing. I say normal, but it's actually the threshold of hearing for people who have very good hearing. For many of us, we can't hear sounds that are actually down at 0 decibels because our hearing has been damaged due to noise exposure, aging, or other factors. 20 decibels is about the background noise in a very quiet room, say out in the country or in a room that's well isolated from any traffic noise, machinery noise, any other sort of noise. A more common quiet room that's not quite so isolated, but there's no one talking, there's no radio or television playing, there's nothing really going on in the room, but there's noise intruding from distant sources. That would be about 40 decibels. Jumping up another 20 decibels to 60 is approximately a conversational level. This is the level that if we typically hear each other talking, that you would set the radio or the television to for a comfortable level, 60 decibels, maybe as much as 65 decibels. Of course, if you have a hearing impairment, you might set it quite a bit higher than this to be able to hear it well. 80 decibels is what most people would consider loud noise. Traffic standing out on the street corner with lots of cars going by. Industrial facilities, very often the minimum noise level is about 80 decibels, even well away from actual noise sources, just the general background noise in the area. Another 20 decibels up to 100 decibels. Most people would consider this very loud. They would probably instinctively put their hands over their ears. Something like a power saw noise level that the user would be exposed to just a couple of feet away from the saw typically would be somewhere around 100 decibels. A couple of feet from a lawnmower engine might also be about that level. When we get up to 120 decibels, now it's extremely loud, and there's potential, at least, for immediate damage to hearing, either in the short term or the long term. Certainly in the short term there will be damage, or at least hearing loss, which will come back probably, but we're getting to the point where it's dangerous. And up at 140 decibels, or maybe even a little lower, 130 decibels or so, we're at the threshold of pain, where the sound is no longer just loud, but it's actually causing the ears to hurt, like something is jabbing them in some way. So we have this very large range of sound pressures which are translated into a relatively small range of decibel values. There are two kinds of logarithms. Base 10 logarithms are also known as common logarithms. These are the ones that are most used in acoustics. The other kind of logarithms are the natural logarithms, which have a base e. E is a number that has the value of 2.718 and so on. On a calculator and in abbreviation, base e logarithms are referred to as LN, standing for natural logarithm. These are not much used in acoustics, so when you're working with decibel values, you want to be sure that you do calculations using the log function on the calculator, not the ln function. Common logarithms are fairly easy to understand. Logarithm of 10 is 1, logarithm of 100 is 2, logarithm of 1000 is 3. So you see it's just a question of how many zeros there are is the logarithm number. On the smaller side, logarithm of 0.1 is -1, logarithm of 0.01 is -2, and so on. One thing that you might not be able to guess is that logarithm of 1 is 0. It's helpful to sometimes remember a few of the easy logarithm values in between these powers of 10. For example, the logarithm of 2 is 0.3. The logarithm of 3 is approximately 0.5. The only thing you can't do with logarithms is the logarithm of 0. That's undefined. There are several rules for manipulation of equations containing logarithms that simplify the work. This is probably the reason that logarithms were invented back before we had calculators, to make some mathematical operations with large numbers easier to carry out. For example, the logarithm of x squared is 2 times the logarithm of x. The exponent, whether it's a 2 or a 3 or whatever else, is just brought out to multiply times the logarithm. The logarithm of 1 over x is equal to the negative of the logarithm of x, or -1 times the logarithm of x. The logarithm of two numbers multiplied together, logarithm of x times y, would be the logarithm of x plus the logarithm of y. So as an example of this, the logarithm of 2x would be the logarithm of 2 plus the logarithm of x. And we know that the logarithm of 2 is 0.3, so it would just be 0.3 plus the logarithm of x. These and other rules are useful in working with acoustical problems because let's look at some examples of how decibel math is different from ordinary math. Suppose, for example, that you had 90 kilogram mass and you put it on the scale and then put another 90 kilogram mass on the scale. So what's the total weight? Well, 90 plus 90 is 180, so it's 180 kilograms. But decibels are different. If you have a 90 decibel noise source, let's say in this little sketch here, machine number 1, producing at the receiver 90 decibels. And then you take an identical noise source, machine 2, which by itself would also produce 90 decibels. What happens when you turn on both machines simultaneously? Well, the answer is 93 decibels. It's not 180 decibels, it's 93. Quite a bit different than the ordinary addition mathematics that we're used to. Let's take another example. 90 kilograms plus 70 kilograms. You just add up the 90 plus 70, that's 160. So if you have both of those weights on a scale, it's going to be 160 kilograms. But 90 decibels plus 70 decibels will only be 90 decibels. Why is this that decibel mathematics is so different from ordinary mathematics? The fact that it's based on logarithms is the reason. Let me try to explain why this is. When two sounds are added together, we're actually adding together their sound power. Power is defined as the flow of energy per unit time per second. The pressures don't add, but the powers do, and the power is proportional to the pressure squared value. So we use W for the symbol for power, and so the total power then is equal to the pressure squared of the first sound plus the pressure squared of the second sound, line 2 there on the chart. Now we know that the formula for the decibel value is that it's 10 times the logarithm of the pressure squared, discounting the constant, which doesn't really enter into the calculations here. And so the total decibel value, summing up number 1 and number 2, then would be 10 times the logarithm of the first pressure squared plus the second pressure squared, line 4. Since pressure 1 and pressure 2 are the same, we can then say that the total decibel value is 10 times the logarithm of 2 times pressure 1 squared. Again, because P1 and P2 are the same. Using our logarithm rules, we can separate the 2 and the P1 squared, and we can say 10 logs of 2 P1 squared is 10 times the logarithm of 2 plus 10 times the logarithm of P1 squared. Logarithm of 2 is 0.3, and 10 times the logarithm of P1 squared is just equal to the decibel value 1. So 10 times 0.3 is 3, plus the decibel value 1 is the total value. So we have two sounds, P1 and P2 are the same. Then we just add 3 decibels to either one of the values. It doesn't matter what the initial sound level was. If there's 2 that are the same, we're simply going to add 3 to each one. So 80 plus 80 is 83, 24 plus 24 is 27, 72 plus 72 is 75, and so on, because our mathematical derivation that you saw there didn't depend on what was the value of dB1 or P1, only that P1 and P2 are the same. Now we've gone through the example where the two sound levels are the same, but as a general rule we can use the same idea for any combination of sound pressure levels. Let's let the power be W, L be the sound pressure level, so the sound pressure level is 10 times the logarithm of W for any particular sound. Taking the inverse logarithm, W then is equal to the inverse logarithm of the sound pressure level L divided by 10, or we can express that as the number 10 raised to the power L over 10. Now when we want to add up levels L1 and L2, we know that the sound powers add, so the sum is just 10 log of W1 plus W2. W1, referring to our previous line, is 10 to the L1 over 10, and W2 is 10 to the L2 over 10. So there's our formula. L1 plus L2 is 10 times the logarithm of 10 to the L1 over 10 plus 10 to the L2 over 10. We can generalize this to any number of sound levels added together. And so I've shown there the total sound pressure level is 10 log of 10 to the L1 over 10 plus 10 to the L2 over 10 plus 10 to the L3 over 10 plus 10 to the L4 over 10 plus however many levels you have that are being added up. So let's take an example. 90 decibels plus 93 plus 91. These are all sound pressure levels that are occurring simultaneously, and so we want to add them up to see what the total is going to be. Now this is pretty easy to do computationally because dividing by 10 is simple. You can do that in your head. And so 90 plus 93 plus 91 is 10 times the logarithm of 10 to the 9th plus 10 to the 9.3 power plus 10 to the 9.1 power. That would be a hard problem to do without a calculator, but fortunately we have calculators, so we go through the math here and we find out that the sum is 96.29 decibels. The same process will apply to any combination of sound pressure levels that we're adding together. Back before calculators were readily available, approximate methods were worked out to make these decibel addition problems easier. They're still quite handy for doing quick and approximate calculations, which are often quite good enough. The idea here is that the difference in the two sound level tells the amount to add to the larger one to find the total. And the chart there on the right shows that with a difference of so many decibels, you add so many more. So the first example we worked out was the difference of 0, we add 3. And that's what we've seen always. 90 plus 90, the difference is 0, so we add 3 to the larger one, so that would be 93. Let's take a few other examples. 70 plus 64, the difference is 6, so according to our chart we add 1 to the larger one, so that would be 70 plus 1 is 71. 80 plus 78, the difference is 2, we add 2 to the 80, we get 82. 99 plus 85, the difference is greater than 10, so we add 0 to the 99, and that's just 99. Now, these are approximate methods. They're not precise, but they're really pretty good. It works quite well and allows you to do a faster method of adding decibel levels than is possible even using a calculator, but you have to keep in mind that it is a little bit more of an approximation. Let's look at some other examples for addition which aren't quite so simple in that they don't fall exactly on the chart. Suppose, for example, we're trying to add 70 decibels plus 66 decibels. That's going to be a 4 decibel difference, so looking at the chart we see 4 is not on there, but 4 of course is midway between 2 and 6, so we add midway between 1 and 2, which would be about 1.5 decibels, so the total will be 71.5. 92 and 93 added together, the difference is 1. Looking at the chart, we're going to add an approximate 2.5 to the 93, giving us a total of 95.5. What about the situation where we have 3 decibel values to add up? 90 plus 93 plus 91, for example. Well, the way we do this is to take any two at a time. So let's say we choose the first two, 90 plus 93. The difference is 3, which is not on our chart, but 3 is pretty close to 2, so we'll add 2 to the 93 and get 95. Now we take that total, 95, and add it to the third one. 95 plus 91, difference of 4. We add 1.5 to the 95, and we get a total for the 3 taken together of 96.5. We can choose another pair at just as well, 93 plus 91. The difference is 2, so we add 2 to the 93 and we get 95. Now 95 plus 90. Well, we see that on our chart here, a difference of 5 is not on there, but 5 is pretty close to 6, so we'll add 1 to the 95, and that will give us 96. So using these two different approaches, we got slightly different answers, 96.5 decibels or 96. And this just merely shows us that it's an approximation. If we had done a better job of extrapolating, we would get virtually the same answer. Now, if we compare the approximate and exact methods for adding up those 3 decibel values of 90, 93, and 91, when we did the exact method, we came out with 96.29. The approximate method, 96.5 and 96. A little difference there, a few tenths of a decibel, but actually these are pretty inconsequential. Typically, we aren't measuring closer than 1 decibel anyway, so being precise in our addition to the tenths of a decibel isn't really particularly necessary. Approximate works just fine. There are uses for that. Exact works just fine, and with modern calculators and computers, it's quite simple. It just depends on the situation, whichever one is more convenient to use, and that's the one you should go with. Why do we need to be able to do mathematical operations involving decibels? Why to be able to add them, subtract them, average them? Well, for adding them, we're talking very often about simulated situations, modeling we might call it, where we're going to make a hypothesis about some situation and see what the result is. So, for example, we have a certain machine producing a noise level to a person. Our simulation, our hypothesis is that we're going to add another machine, or maybe 2 more machines, and see what the effect is on the noise level at that given spot. One can imagine very complicated situations, like, for example, a highway where it's producing a certain amount of noise, and we're going to add some additional traffic on this highway. Some more big trucks, which will produce a certain amount of noise, more cars. So that sort of thing is an example of where we need to be able to add decibels from the sound levels from different sources. One very common other situation is when we're combining the various frequency bands of noise to determine the overall sound level. So when you're looking at a particular sound, it's broken up into many frequency bands. As we do something to the sound, make some noise control steps, the different frequency bands will be affected in different ways. And then to find the overall sound, as a result of those changes, we have to be able to add back up the frequency bands. So there's another common situation where addition is needed. Subtraction is also needed in the simulation and modeling area. I guess fairly obviously, we have several machines. We take out some acoustically or physically. So what's the resulting sound level going to be? So we're subtracting their sound level, and we want to be able to compute the result. Another common situation for using subtraction is to adjust for background noise. Suppose we want to know the noise output of a certain machine, and it's in the midst of a factory where there's lots of other stuff going on. Well, one approach would be to shut down the whole factory and just run the machine of interest by itself. However, that's very often not practical. So instead, what we do is measure the machine plus the surrounding sound, the background noise, then turn the machine off and measure just the background noise. Then we're able to mathematically subtract that reading from the total sound, and the difference will be just the noise from the given individual machine we're interested in. So that's a very common use for subtracting decibels. Averaging decibels is also frequently done, either in terms of a spatial average, where we want to average the noise over a certain area that people may be moving around in, which determines their exposure to the noise, or even more commonly on a temporal or a time basis, where the noise level is varying throughout a given time period, and we want to know what is the average level that a person is exposed to throughout that time period. And so we have to have a way of mathematically averaging the sound. Addition, subtraction, and averaging are all very similar mathematically, and we will go through the various steps to show you how to do that. Subtracting sound levels is very similar to addition. In fact, it's exactly analogous, with the only difference being the minus sign in the equations. So the difference between level 1 and level 2 is 10 log of 10 to the L1 divided by 10 minus 10 to the L2 divided by 10. Unlike addition, however, we don't have more than 2 at a time. That doesn't particularly make any sense, so we just take it 2 at a time. For example, if the total noise in an area is 90 decibels, we turn off a particular source, and the background or the total noise then drops to 80 decibels. When we do our subtraction, that would be 10 log of 10 to the 9th minus 10 to the 8th. And if you go through and do the calculation, that's 89.54 decibels. Or in real life, we would normally average that off to 89.5. And that would be the noise output of the machine that we had just turned off. Another example, 90 minus 83. You can see the calculation there. And the sum is 89.03 decibels. And again, we would just use that as 89 decibels. So the process is just like addition in terms of the exact calculation. There's also an approximate method for subtraction, which is very similar to the approximate method for addition. We simply look at the difference in the two sound levels that we're subtracting. It tells us the amount to subtract from the larger one to find the remainder. And the table on the right there shows you the difference between the two levels and the amount we subtract from the larger one. So if the difference is 1 decibel, we subtract 7. If the difference is 2, we subtract 5, and so on. So here's an example. 70 minus 63, the difference is 7, so we're going to subtract 1 from 70, will give us 69 decibels, is the difference in 70 and 63. Another way of looking at this, or a way to check it, would be 63 plus 69 would be 70. 80 minus 78, difference is 2, so we subtract 5 from the 80 decibel, and gives us a difference of 75. 99 minus 85, the difference is greater than 10, so using the last line of the table, we subtract 0 from the 99, so the difference is 99 decibels. 91 minus 90, the difference is 1, so we subtract 7 from the 91, and we get 84. So this is a pretty simple way to approach this, and the approximate method works just fine for most practical cases. There's a potential difficulty with doing the calculation regarding subtraction, whether you're doing it exactly or approximately. This has to do with the situation where the two sound levels are close together. For example, you're doing a background noise measurement and the total noise is 91, and then you turn off the machine of interest and you have 90 remaining. Now, according to the table here, 91 minus 90 is 84 decibels. If we were to do the exact method, we would get 84.2. So that's quite close. However, suppose that instead of 90 decibels, the true sound was 90.5. A 0.5 decibel measurement error is quite easy to make. Most instruments are only accurate within 1 decibel anyway. Now, if we were to use the exact method and subtract 90.5 from 91, that will give us 81.4. So if the true value is 90.5 and the true value for the total is 91, then the true value for the machine noise is 81.4. So you see how a half a decibel measurement error, the difference between 90 and 90.5, leads to about a 3 decibel calculation error. This is unsatisfactory, so we try to avoid making our calculations based on small differences like 91 and 90 decibels. As a guideline, most people will try to make sure that the difference that they're looking at is at least 3 decibels to get reasonable accuracy. Averaging sound pressure levels is also very similar to the exact method for adding and subtracting. There is no simple approximate method we could use, so we have to use the exact method, in which we simply add the sound powers up, the 10 to the L1 over 10 plus 10 to the L2 over 10, and so on. And then before we take the logarithm, we divide by the number of sound levels that we're adding up. So it's the usual idea of an average. You sum up all the values and divide by how many values there are, except that you do it before you take the logarithm. So for example, to average 90 and 80 decibels, we take 10 logarithm of 10 to the 9th plus 10 to the 8th divided by 2. That gives us an answer of 87.4 decibels. Why is the average of 90 and 80 not 85, as it would be if they were ordinary numbers? Well, it's because they're not ordinary numbers. They're based on logarithms. And 90 is a whole lot more than 80. It's 10 times as much sound energy. And so the average will not fall in the middle, but it will be weighted more toward the top. So that's the reason we get 87.4 instead of 85. Sometimes a simple average is just fine. For example, if you're doing a spatial average and you make 10 readings all around a given room, and there's an equal probability that a person will be in any spot in the room, then all we need is a simple average. Or you might do a time average where you make equal time measurements, 1 minute here, 1 minute there, 1 minute over there, and so on. But quite commonly we have to do a weighted average. And a weighted average is just like the average, except that each value, each sound power, gets a certain weight, and then those weights are added up, and that's the number you divide by. So there's the rather complicated formula with the weights shown in red on the screen. Now these weights could be just simple numbers, like there's 5 times as much area for level 1 as for level 2, and so W1 would be 5 and W2 would be 1, that sort of thing. Or they could very often, and most often, be times. The result of time weighting is often called the equivalent sound level or the equivalent continuous sound level, L sub EQ, or just the LEQ. The LEQ is defined as the sound level over a given time period that would give the same sound energy as all the varying sound levels that actually took place during that time period. So it's a way of substituting one value on an energy basis for a large variety of sound levels and simplifies our life in terms of noise exposure. So let's take an example. We have a person exposed to 90 decibels for 5 minutes, then 80 decibels for 55 minutes. So our weights are 5 for 90 and 55 for 80. We put them into the equation, as you see, and the result is 82.4 decibels. The actual unit of time doesn't really make any difference. That could have been 5 seconds, it could have been 5 hours, it doesn't make any difference as long as we use the same units. We couldn't use 5 minutes for 90 decibels and then 1 hour for 80 decibels and expect to get the right answer. We just have to make sure they're in the same units, and then we'll get the correct answer for our LEQ. There's another weighted average that's often used, particularly when calculating the average noise exposure according to OSHA rules. This is called LOSHA very often. It's just like the ordinary time-weighted average that produces the LEQ, except that where the figure 10 appears, in most cases, we substitute 17, or to be slightly more precise, 16.61, although it makes very little difference which one of those two numbers we use. So now we have an even more complicated formula for computing the average, and this is done because OSHA didn't want a strict, true time-weighted average based on their epidemiology studies. At the time they enacted this rule, it was decided to make a slight change, and this is the change that was made. So if we put the numbers in the formula just as we did for the LEQ example, 90 decibels for 5 minutes, 80 decibels for 55 minutes, we get the LOSHA is 81.6 decibels rather than the 82.4 that we had for the LEQ for the same sound level at the same time. It's just a question of a strict time-weighted average versus a modified one used by OSHA. Now this is pretty complicated and gets tedious to do the math, but you should keep in mind that one very seldom has to actually do this math. The instruments themselves have the formulas built in and do the calculations for you. It's more a question of understanding how to do it so that one could, if necessary, make the calculation for a simulation or a modeling situation. Suppose in actuality we had this sound level and another sound level and a third sound level, and we want to know what happens if we change one of those sound levels. So it's a what-if situation that we would be using this kind of equation for. For actual measurements, the instruments do it automatically for us. And if we need to do the calculation, computer spreadsheets are a very handy way to do it so that we can put in our formula, make our changes as needed, and come up with the right answer without too much trouble. To summarize, we've learned that the sound pressure level is a logarithmic transformation of the root mean square acoustic pressure value. And we use the root mean square in order to deal with the problem of the average being approximately 0. The unit for sound pressure level is the decibel, small d, capital B being reminder of Alexander Graham Bell, for whom it was originally named. Typically encountered range is from 0 decibels, the threshold of hearing for very good ears, up to 140 decibels, threshold of pain. Although most of the time we're in an environment from, say, 40 decibels, a quiet room, to 100 decibels, a really loud environment. Decibel units can be added, subtracted, and averaged, but done using special rules involving logarithms. We add them, subtract them, and average them for a variety of reasons: modeling, measurements, exposure assessment. And lastly, the sound pressure level is an indication of the sound power, which is the rate of energy per time, and of the sound energy if we integrate over a specific time period.